Welcome to Spring LIB.
Hello, today we're talking about a problem where we have a mass on a spring and it's in the middle of its motion and we don't know where that is in relation to the amplitude and the maximum velocity. So for this problem, we're really kind of trying to figure out what a strong tool energy conservation is. So we'll start off with part A. Part A asks us to find the amplitude of motion with energy conservation. So first thing we're going to do is we're going to write down the energy that the spring has at this position that it's at. So we can say that E naught is going to be equal to 1/2 times the spring constant times x naught squared, the position that it's at, which is the potential energy of a spring, plus the kinetic energy, which is going to be 1/2 m times v naught squared. To find the amplitude, we're going to be looking for where x is at a maximum. So we're looking for where there's no kinetic energy contribution and it's all potential spring energy. So we're going to set this equal to 1/2 k times the amplitude squared. So we're going to do basically we're just going to solve all this for the amplitude. When we do that, we get that the amplitude is going to be equal to the square root of the mass divided by the spring constant times the initial velocity squared plus the initial position squared. If you plug all that in, then you get the answer as being 0.041 meters. But the problem gave it to us in centimeters, so we're going to give it back to them in centimeters and say that it's 4.1 centimeters. Cool. Part B is asking us for the maximum velocity. So we could set up the problem just like we did in part A, where we say we have an initial position and an initial velocity, and we use it to solve for the purely kinetic energy. Another way you can do this, though, that's a little bit simpler, is say that this thing that we found out last time, 1/2 k times the amplitude squared, is going to be equal to 1/2 times the mass times the velocity squared. And this is, of course, V max. This is a little bit simpler, and it still works because if two things are equal to one thing, then they're equal to each other. We do a little bit of solving for V max, and we get that V max is going to be equal to the square root of k over m times the amplitude squared, which in this case is going to be 1.21 meters per second. Cool, and then we're going to go on to part C. Part C asks for the angular frequency, omega. We have a really good expression for omega. Omega is just going to be equal to the square root of k over m. This has been in all of these problems up to now. So we can just say that this is going to be equal to 29.76, and then the radians per second. Always important to remember the units for what you're looking at. So that's how you do this problem, and I hope this helped.